Okay, now it's recording. Looks like everything is moving and is in order. Now let me go ahead and share my screen. Please let me know if you can see that. Yeah, thumbs up. Okay, cool. All right. So for this first problem, liquids in a U-shaped tube. Liquids in a U-shaped tube. So it says a U-shaped tube is partially filled with water. A volume V of a liquid with an unknown density is then poured into the left side, and the surface of the unknown liquid ends up higher than the surface of the water on the right side. Okay, so we have this liquid here, unknown density, we're not sure about the density for it. It's poured into the left side, and then the surface of that unknown liquid ends up being higher, has a higher height here, like at least relative to this point. It's a little bit higher than the surface of the water on the right side. So for part A, there's not much information that they give you here, except that density, this is rho, density of the liquid is less than, or at least that's left and right, but density of the liquid is less than the density of water. Or we can say that rho L is less than rho R. So for part A, they're asking us, is the density of the fluid larger, smaller, or equal to that of water? Is the density of the fluid larger, smaller, or equal to that of water? Right? Oh, hold up. Did I already say what it was? I think, my bad. No, hold up. I just read the problem wrong for some reason. But I saw density, I saw lower, and I completely messed that up. I'm sorry. It's the heights that are different. My bad. Not the densities. We don't know about the densities yet. That's what we're going to figure out in part A. My bad. Height L. No. So we haven't gotten to. Let me just rewrite what I said for part A here. My bad. So the volume of that liquid has an unknown density. It's poured onto the left side, and the height L is greater than height R. That's what I meant. So the height of the liquid is greater than the height of the water. That's my bad. So I don't know why I referred to density there. I just totally misread that question. But part A is asking density of the fluid larger, smaller, or equal to that of water. So they're now asking us about this rho L, right, the density of the liquid on the right, versus the density of the water, right? Is it larger, equal, or smaller? Anyone have any ideas here? Mm-hmm. Yeah, no, I understand what you're talking about. Yep. So that what you're referring to is Bernoulli's equation, right? So, or at least part of it is Bernoulli's equation. So, PA, so the pressure at point A plus the density of the liquid, right? Times the gravity times the height A is equal to point B, or at least the pressure at point B plus the density times gravity times the height at point B, right? So in a sense, that's at least part of what's going on here, right? it's definitely a factor, and we can look at that, right? So number one, though, Kimberly, you're absolutely on the right track. So we're looking at like points A and point B, for example, right? Or at least like let's look at here and here. So these 2 points here are both in contact with the atmosphere, right? So this point here, this point there, they're both in contact with the atmosphere. They're both in contact with air. So we should actually expect the pressure to be the same at those 2 points, right? Because they're both in contact with the atmosphere. Right, so technically P atmospheric for both of these sections here. Now, the thing is, this point with the water, based on our knowledge, right, when 2 points in a liquid, right, are at the same height, they should have the same pressure. So the idea here is to compare the 2 pressures here and here, for example. So if we look at that, let's say this is pressure 1 and this is pressure 2, right? So pressure 1 is for the fluid at that specific height. So that would be equal to the density of the fluid times the gravity times the height at L there. Oops, my bad. Or actually, you know what? Let me adjust that. Let me say, let's compare these 2 heights. My bad. Let's compare these 2 heights there. So that way you're comparing the full length of HR. So we have pressure at point 2 and pressure at point 1. So we know that P1 is equal to P2 because they're at the same height. We know that for sure. Now, at P1, we can say it's the pressure there is the density of the fluid times the gravity times the HL there, right? That would just be the distance or the height downwards like that. And then pressure 2 for that water, right? It would be the density of the water times gravity times the height of the water, and they refer to it as HR, as in like the right side. Now, if we're assuming that these 2 pressures are equal since they're at the same height, pressure 1 and pressure 2 are equal since they're at the same height, then if we were to basically kind of like set these equal to each other, right, P1 is equal to P2, then the density of the fluid times GHL should be equal to density of the water times GHR, right? Now, the idea here is that your gravity should cancel out because it's a constant value, so they wouldn't factor in. Now, HL versus HR, well, we know that HL is definitely a lot bigger than HR, right? So if this is larger than HR, then we can see, for example, that these densities would have to be different. How are they different? Well, if we were to technically, like, say if we increase this, right, and we decrease the height on the right, then in order to maintain the same pressure for the values to be equal on the same side, right, we can say, for example, like, this is just basic math. If I said that P fluid times G is 3, right, and height L is equal to 4. So 3 times 4 is equal to 12. That's my P1, for example. Well, I want to make sure that P1 and P2 are equal to each other, right? So if I want to get 12 on this side as well, I know that my HR is actually, smaller than my HL. So the height on the right side is smaller. So let's say this height was 2. In order to keep 12, have a product of 12 on that right side, then this has to be 6. 6 times 2 is 12. So you can see 6 versus 3. If I have a larger height over here and a smaller height over there, 6 times 2 versus 3 times 4. You can see that the height, HL, is greater than the height of HR. And so thus, the density of the fluid should be smaller than the density of the water. So density of the fluid should be less than the density of the water, right? Because the height on the left, right here, is going to be greater than the height on the right. In order to maintain the pressure on both sides for P1 to be equal to P2 at different heights, then the density of the fluid, this unknown liquid, let's say it's oil, for example, has to be less than the density of water, right? And so if we were to use this equation that Kimberly mentioned earlier, right, we can do the exact same kind of thinking, right? PA versus PB. This is 0.1, this is 0.2. PA, PB, right? Same thing. We know that the pressure at that point, at this interface between the oil or between the liquid, right, and the water is some pressure. And then at 0.2, which is the water, right, for PB, it's the same pressure. Pressure will be the same at the same heights. So if this was like 10 meters upwards or something like that, they're at the same height to each other, and so they should have the same pressure. All right, that's a rule that we know. And so if PA is equal to PB, well, if you just subtract them on both sides, they should end up canceling each other out, right? So this is like 10 pascals, and this is 10 pascals. Well, if you subtract 10 pascals on the other side, this goes to 0, this goes to 0, right? Now you're just left with rho GHA, so the density of fluid A, or density of the liquid, right? Times its gravity, times the height at that liquid. And then same thing over here, but with water, right? Like I said, since you know that HL is larger than HR, so HA is larger than HB, then in order to maintain the same values on this side and the same values on this side, if G is constant, HA is bigger, HB is smaller, right? In order to have the same kind of cancellation, then we have to have a downward arrow here, upward arrow there, right? So your density of your water has to be larger in this case than the density of your liquid. So think about it like I said, if HA is 4 meters, for example, HB is 2 meters. So we know that HA is larger than HB, or HL is larger than HR. Then if we were to say that the product of PG, or rho G, right, your density times your gravity, if that product was 3, for example, so 3 times 4, that gives you 12 on this side. If I wanted to maintain 12 on this side, then I make sure that my product of density times gravity is 6 as well. Well, gravity doesn't change, so the only thing really that I'm changing is my density. So therefore, my density has to increase on this side. And so density of water would then be equal to, or my bad, greater than the density of the fluid or the liquid, right? So excellent job on noticing that it's a hydrostatic pressure equation there that we're using, right? And this is, like I said, this is a component of Bernoulli's equation. It's a very large component actually to it. Now, kind of a side note, this is like kind of MCAT stuff, right? This component right here, the pressure at a specific point plus like the density times the gravity times the height at a specific point, this together is what is called static pressure. And once you go to Bernoulli's equation and you add that other component, which is half times your density, right? Times your speed squared. Once you add that component alone, the half density times speed squared, we call that dynamic pressure. And that's just the pressure associated with the movement of a fluid. So this is static pressure, just the pressure associated with a fluid stationary, static, right? And then this component, half times density times v squared, is your dynamic pressure, which is the pressure associated with the motion of a fluid. And that'll help to understand a specific component of like flow and stuff once we get to this part right here. but does that make sense as to why the density of the water is greater there? I see one thumbs up. Did that make sense as well, Kimberly? You were right on the dot there with that equation. So excellent job. Okay, cool. Thumbs up. Awesome. Alrighty. So that's that first aspect there. Now with part B, it says determine the density of this unknown liquid if HR is 11 centimeters and HL is 16 centimeters. So now they want us to find out the density of the unknown liquid actually. So how do you think we're going to be able to find the density of the unknown liquid in this case? Yeah, once again, use the hydrostatic pressure equation, right? And we can kind of use the same points as well again, P1 and P2. While we look at P1 and P2, we know those should be the same pressure because they're at the same height. So we can say P1 plus rho GH1, or HL essentially at that point, P2 plus rho GH2, my bad, not 2, I keep saying 2 and 1, HR, right? Because we want to use, we want to be able to use these values here that they have, and which will correspond to these two pressure points, because here's HL comes at this pressure point, here's HR comes at this pressure point. So for this equation here, we know that P1 should be equal to P2, so they should cancel each other out. And so then you're just left with rho GHL is equal to rho GHR. And so we know that the density here is the density of the water, right? Density of the water, oops. Density of the water over here. And so density of water is a constant 1,000 kilograms per meter cubed. That's the density of water, right? And then we multiply by the acceleration due to gravity, which is 10 meters per second squared, and then times HR, which is 11 centimeters. We want to convert that to meters so that we have SI units, and that's just 0.11 meters. And then for the left-hand side here, well, we don't know the density of the liquid yet. We do know that acceleration due to gravity is 10 meters per second squared, and that HL is 16 centimeters, which is 0.16 meters, right? So if we go ahead and solve for that, we should get a density of the liquid that is 687.5, I believe, kilograms per meter cubed. Does that make sense? Yeah, I can zoom out, my bad. Sound good so far? Okay. So that's the density of the unknown liquid. For part C now, they're asking, or they're saying, if the liquid was replaced by the same volume of a liquid with even less density, what would happen to HL and HR, right? So if we were to have a liquid there with even less density, so remember earlier, right, since we said, okay, well, the height at L here, the height L here is greater than HR. And because of that, since the height on the left-hand side was greater than the right-hand side, then the density of the liquid, we said the density of the liquid was less than the density of the water, right? We said that since H, if H increases on the left-hand side and H decreases on the right-hand side, then the density, right, of the liquid is smaller than the density of the water. Water, and here's the liquid, right? So it's kind of like an up and down kind of procedure. They're just kind of compensating for each other. The density goes down on one side, then the height has to go up, right, to maintain a specific like pressure, maintain a specific value, right? So in this case, if they're asking us now, okay, well, what if we just kept the heights the same? What if we kept the heights the same and we didn't change them? And now we just want to change and mess with the densities a little bit. How does that now change the height? Right? So if we kept these heights, for example, 11 centimeters and 16 centimeters, we didn't play with the height anymore, right? And now we're just playing with the density a little bit. How does the density now, if we were to decrease the density on the left-hand side, that density went down even further from 687 to 500 or something kilograms per meter cubed. How would that change up your heights? So which heights would increase? Which heights maybe would decrease? Can you be a little bit more specific? So you got the HR part absolutely right. HR would decrease. HR would decrease, right? And so that's excellent, right? Because it's very similar to what I said earlier. So if we have this side here, this density, it went down, right? And we're maintaining the same density over here, right? Because we're not changing the type of liquid or the type of fluid, the type of water. So densities will remain the same, at least like for the water side. So if we decrease the density of the liquid, gravity's constant, right? Now, let's say again, like if I did the that math type problem, right? If I said this was 3 times 4, right? And now all of a sudden I want to make it 2 times 4, right? So I go from 12 to 8 now. Now, if this was initially, if this density was, let me actually, okay, so just so I can make sure that I'm getting that right. So we said that the density of the liquid was already less than the density of the water. So let's say that was 3 for the density of the liquid and 6 for the density of water, right? Now, if we wanted to, let's say here that the height was 4 and this was 2 for the height of the water. Now, if we were to decrease the density even further for the liquid, if we dropped from 3 to 2, right, we changed our product. Now we're not maintaining the product, we changed it up. So from 3 times 4 to 2 times 4. So from 12 to 8. In order to get 8 over here, how can I do that? Well, like Matthew said, we would have to mix up the height a little bit, right? The heights would have to change because water is water, right? You didn't change like anything about the properties of water itself that would cause it to have a different density. So water is water. 6 is 6 for your density. What can I do to basically like mess with this product here to get it from 12 to 8, right? Well, then I'd have to change up the height. So 6 times what, for example, in that case, would be equal to 8? Well, it would be just 8/6 in that case, right? And whatever that is, right? That's what? 4/3? That's like 1.333 something, right? So you can see then that the height on the right would decrease. Cool, awesome. Height on the right would decrease. However, all they said was that we're just decreasing the density of the liquid. But the volume was the same. Volume, as we define it, is equal to a specific area times a specific height. So if we keep the volume the same, Well, the area of the tube, remember, like this is going to be like a graduated cylinder type deal here, or kind of like a cylinder shape. So the area would just be like the cross-sectional area, the area of a circle, and then multiplied by the height. Well, if we're maintaining the same volume of a liquid, since the tube is the same, the height has to be the same. Since the area of the tube is the same, we're using the same tube, we're not changing up the tube or anything like that, and we're maintaining the same volume of liquid. Since we're maintaining the same volume of liquid, and the area of the tube is the same, then the height has to maintain the same. So in essence, it's not the same idea as A, because A, in part A, we were changing up like heights in order to maintain a specific product, in order to maintain a specific value. Remember I said 3 times 4, oh, well, if I want to change up the height for the water to maintain like a specific pressure, right? 3 times 4, okay, then 6 times 2. So a difference in height and a difference in density in order to maintain that product of 12 on either side. But the idea here for C is that, okay, well, we're just solely going to mess with the density, right? We're just going to mess with the density only. So if you mess with the density and you're maintaining the same volume of the liquid, well, the volume is just going to be based on the area of the tube times the height of the tube, right? That's just the volume of liquid that you input. So if I only fill it up to here halfway, well, I inputted, or I poured in like less volume of water. So this might be like 30 milliliters, and up here would have been 60. So I'm still putting in that 60 milliliters, for example. I'm still putting in that same amount of volume. It's just that now, instead of messing with like the heights and stuff, I'm going to be messing with the density. So I'm still keeping that same volume. So therefore my height has to be the same. So for this term here, rho GHL, height stays the same, gravity's constant, so it stays the same. I'm just decreasing density, right? So if I just decrease this density side, so if I was 3 times 4 at first, like this group here is 3, and the height here is 4, right? If it was 3 times 4, then all I did was just drop down the density from 3 times 4, now 2 times 4, right? So instead of 12, I get 8. So the idea here then is that on the right-hand side, I still have the same density of water, right? Let's say the density of water was, like we said before, that it was greater than the density of the liquid. So here's the density of the liquid, that was 3. The density of the water was 6, right? If I had 3 times 4 at first, 4 was my height, HL. This is density of the liquid, this is density of the water, height of the water, right? So if I drop down my density of the liquid to 2, and I kept the height the same because I'm pouring in the same volume, then instead of 12, I have 8. Well, I'm still pouring in water, right? Water has specific constant properties. Its density shouldn't change. So I'm pouring in water with a density of 6, for example, just theoretically, right? Well, at first, in order to maintain that 12, I had a height of 2 for my water. Well, now I'm not maintaining 12 anymore. I have to have a new product here, which is 8. So instead of having to change like the density and stuff like we did before, then we have to change the height. And so now your height drops down to like 1.33 instead of 2. So to kind of properly sum that up and use equations to formally say it, right? If that liquid was replaced with the same volume of liquid that has even less density, then we would see the height on the right-hand side decrease in order to compensate and make sure that the pressure at that point at the bottom of the liquid, right, here and here, to make sure that these two pressures stay the same. So if I drop down that density, it goes from 12 to 8, then I want to make sure that I still have that same 8 value. So if I poured in some new liquid and all of a sudden the pressure point here becomes 8 instead of 12, then I want to make sure I have 8 here. In order to have 8 here, right, then I have to change up my height of the liquid. So maybe the height here would drop down like this, to where at that point P2 you would have a different pressure that would be brought down from 12 to 8, for example. So let me actually type it up here just so you can have like a very nice and neat and organized kind of explanation for that. So, if the liquid was replaced with a liquid that was even less dense, but the same volume was poured in, right? Then we would see the height on the right-hand side decrease to compensate and ensure that the pressure at P1 is still equal to P2 with those pressures labeled above. So you can say like, oh, pressure P1 and P2 are the pressures that you labeled up here as P1 and P2, so that it's clear for the TAs. And so based on the equation, right, based on the hydrostatic pressure equation, if P1 is equal to P2, then you have like P1 plus PGHL is equal to P2 plus PGHR. Oops, PGHR. And then that gives us just PGHL. I just say P. It's rho, but you know, you get the idea. Densities. Right, it looks like a fancy P. So PGHR, right? Because the P1 and P2 will cancel out on either side because they're the same pressure. We can see that a decrease in density of the liquid would result in a simple decrease in the height of the water to ensure that the pressure remains equal on both sides, right? The height on the right would decrease to offset the density decrease of the liquid to make sure that the pressure is the same. The height of the liquid, though, will remain the same because the same volume of liquid is kept, right? Or because we kept the same volume of liquid. And so then you can refer to the volume equation, right? Volume is equal to area times height of the liquid, right? If we poured in the same volume and the area of the tube didn't change, then the height of the liquid should not change either. But that's kind of like, that would be like the formal way of summing everything up with equations, with relating everything. And please do like use the equation in your answer just so you can have like a reference essentially for the TA so that they can see that you're applying the equations properly and that you can understand like what's going on and how these variables are relating to each other. But excellent job, Matthew, on recognizing that the height there on the right decreased. The only thing that like don't worry, like personally I messed it up when I did this homework. I think I like missed a point on part C just for saying that the height on the left decreased. Because it's really easy to overlook this part of the question, which is they put in the same volume of liquid. So if the same volume is equal to area times height, well, the area of the tube that you're pouring into didn't change. The cross-sectional area didn't change. And so if you're pouring in the same volume, right, same 60 mils, same 100 mils or whatever, right, milliliters, then if you didn't change that area of the tube, the height shouldn't change if you want to keep the same volume. So height on the left doesn't change. Height on the right will decrease in order to compensate for that density decrease, to maintain that same pressure at P1 and P2. Does that make sense? Mm-hmm. Yeah, and HL stays the same as well. So the height on the left would stay the same, and height on the right would decrease. Sound good? Sound good for everyone else as well? Does that make sense? Yeah, this is all because of the volume of the liquid having to stay the same. Because you poured in the same volume, you're going to keep the same height of the liquid. And so if you're just changing the density on the left-hand side, like if you're just changing this density, if you're decreasing it, and the height stay the same and the gravity stays the same, well, if you're also pouring in the same amount of water, then you're not changing the density of water and you're not changing the gravity. And so then your height has to decrease. So if you see a decrease in density, you have to see a decrease in height, because the volume is kept the same, so the height of the liquid is kept the same, and you're pouring in just the same type of water, right? You're not pouring in like really heavy water or really like thick water or anything like that, right? So it's just the same water, and so the density of water should stay the same, gravity should stay the same, gravity here should stay the same, height here should stay the same because of the volume. And so if you're decreasing the density on the left-hand side, you also would have to decrease the height on the right-hand side in order to make sure that the product and the pressure on both ends would be the same. Cool? Okay, cool. Then we can move on to part D, right? Part D is saying the density of the unknown liquid is now decreased to half of what it originally was. Now we just have to find out HL and HR, right? So remember, this is kind of a continuation of part C. Well, if just the density is what we're messing with for the unknown liquid, then what should we observe here for part D? What should change and what should be kept the same? Would HL increase if we're just messing with the density of the liquid? No, right? Because remember, what we said here is that if you're just messing with the density and you're keeping the same volume, then your height would stay the same for the unknown liquid. But HR would have to decrease, right? Because if we decrease, remember what we said here, if we decrease the density, then the height on the right-hand side would also decrease. Now we're just figuring out exactly how much that decrease is, basically. So if we had that same equation set up earlier, P1 plus rho GHL is equal to P2 plus rho GHR. P1 and P2 are the same height, so they should cancel out. Same pressure there. So you're just left with rho GHL is equal to rho GHR. Your density of water is known, right? That was 1,000 kilograms per meter cubed. Gravity is 10 meters per second squared, and now we want to figure out what HR is. Well, we know that HL is going to stay the same because we're putting in the same volume, right? We're just changing up the density. So if we half the density. Remember, the density was initially 687.5. So if we take that and multiply by 1/2, right, that ends up being 343.75 kilograms per meter cubed. That's our density for the unknown liquid, multiplied by gravity, which is 10 meters per second squared. And then we maintain that same height on the left-hand side, which was 16 centimeters, right? So that's 0.16 meters. So if we go ahead and solve, we can see then HL will maintain the same, 0.16 meters or 16 centimeters, because we're putting in the same volume. We're just messing with the density. And HR now will be a lot smaller. It'll instead be 0.055 meters, right? Which is around 5.5 centimeters, right? So it went from 11 centimeters to 5.5, pretty much cut in half. So that's HL and HR. But yeah. Now, we had an additional question. We had part E. It's basically the opposite of C. So instead of replacing the liquid with the same volume with less density, what if we replaced that unknown liquid, same volume, but higher density? How would HL and HR compare? Let me ask, let me see how I'll ask on someone this time. Or call on someone, my bad. Let's see here. Anjali, do you want to give it a shot? Am I pronouncing that right as well? I just want to make sure. Not sure? Okay. Do you want me, I can repeat the question as well if you want. Yeah, Carlos, I can repeat the question just to make sure that, like, 'cause I just want to make sure that you guys are, like, not leaving problem one without understanding, like, this stuff. So the question is if we reverse the conditions for part C. So if the liquid was replaced by the same volume of liquid, but with greater density instead of less density, so if we increase the density of the unknown liquid with the same volume, but increase the density, what would happen to HL and HR? And please feel free for anybody else who is, yeah, if you guys want to chime in as well, like, just so we can keep things moving. So if we replace with the same volume of liquid, but greater density, so same volume, but greater density, would HL decrease? Why do you think it's going to decrease, Kimberly? Yeah, so if density is increasing, remember density is mass over volume, right? If I'm just playing with the density and I made it greater, then, for example, if we go by the definition of density, then I might be decreasing the volume, right? But I already said in the condition that I'm keeping the same volume. So if I keep the same volume, right? So the volume stays the same, then in order to increase density, I would increase mass, for example, right? So I might just add, like, I don't know, just more like mass of water, I guess. But like I said, if I'm keeping that same volume, remember we said volume was area of, like, the tube, right? Or area of, like, the cross section there times the height of the tube, basically. So if I'm keeping the same volume, should I see any increase or decrease in the height? No, right? So if we're keeping, it's the same tube that we're pouring into, same cross-sectional area. And so if this is 10 basically, and this is 5, well, this is 2. If I pour in another 10 and the same area of the tube is 5, this is also going to be 2. So it shouldn't change, right? Now that we got that out of the way, right? If the volume is the same, 10 and 10, HL would remain the same, 2 and 2, because the area is 5 and 5, right? That's just, if we're like doing some theoretical like math there, right? Now, if I increase the density, of the unknown liquid, what happens to my HR here? This is also assuming that I keep the density of the fluid the same, because I'm pouring in the same water, right? So if I increase the density of the liquid, the unknown liquid, this is the same, this is the same, this is the same, and this is the same. What would happen to my HR? Increase, right? Excellent. Yep. So if we increase the density, we increase the HR, assuming that everything else stays the same. We're pouring in the same amount of water, the same type of water, right? Or at least, yeah, same type of water at least. Yeah, same type of water. So the density stays the same, gravity stays the same, gravity stays the same. We're decreasing the density of the liquid, right? And the height stays the same because we're pouring in the same amount of volume. So now, what's left here really is to increase the height, increase the height. If we're increasing this, we increase that. If we decrease this, we decrease that. Assuming that gravity is the same, height is the same because we're pouring in the same amount of volume. We're pouring in the same type of water, so the density stays the same. Gravity is constant. So if we increase density of the fluid, then we increase the height of water. If we decrease density of the fluid, we decrease the height of water. Does that make sense overall? Okay, cool. Now for problem 2, move on to that one. It's blood flow. It says the carotid arteries carry blood up through the neck to the brain. In one patient, they are 11.2 centimeters long and have an inside diameter of 5.2 millimeters. Assume the speed of the blood at the bottom of the artery is 0.5 meters per second, and the density of blood is 1,050 kilograms per meter cubed, right? So the speed is 0.5 meters per second. Density of the blood is equal to 1,050 kilograms per meter cubed, right? The length is 11.2 centimeters with a diameter of 5.2 millimeters. Okay. Now for part A, they're saying by what amount does the pressure drop in one of these arteries from bottom to top? So what is the pressure difference basically from top to bottom, right? P top minus P bottom. What would the pressure difference be? So if we wanted this P top, P bottom, that would be essentially delta P, right? So difference between the top pressure and the bottom pressure. So anyone have any suggestions as to how to start these? I know these are all like very kind of complex problems, so like even if you guys have like at least like one step or one idea, we can kind of go from there. You don't have to like have the whole thing figured out. That's excellent though for part B though. We can get to that for part B for sure. But yes, we would use the hydrostatic pressure equation again. if we want to figure out differences in pressure, right? So remember, like, if you're thinking about like differences in pressure or anything like that, we can kind of think about this kind of situation where we're like looking at different heights and stuff to compare the different pressures at different points. So if we were to draw it from top to bottom, right? Because normally you think of an artery kind of going from like left to right. Like usually you see them in like cross sections, right? For your anatomy textbooks or your biology courses or whatever. You usually see an artery kind of like left to right, I guess, or at least drawn left to right, especially for like diffusion and whatnot. But if they're going top to bottom, then we can say it kind of looks like this, right? So just a cylinder, basically, top to bottom, right? So this is, let's say point A is top, point B is bottom, right? They said that the length of the carotid arteries are 11.2 centimeters, right? So this whole thing would be 11.2 centimeters. Well, what do you notice? 11.2 centimeters in this case, like at least from this perspective in the drawing, would not be our length, but it would be our what? Height, exactly. So 11.2 centimeters is our height now, right? Now, if we use this hydrostatic pressure equation, right, we said PA is the top plus rho GHA, oops, not plus, is equal to PB plus rho GHB, right? Well, everything is kind of internal to the body here in this situation, right? Normally, right, if we have a problem like this and we said that, okay, the water is in contact with the air or something, then the pressure here at the top would be atmospheric pressure. But everything's kind of internal. And so we can't really say, for example, that pressure up top here is equal to atmospheric pressure or something like that, right? Can't really be sure. But what we can notice is that they're asking us for P top minus P bottom. P top minus P bottom, the delta P, the pressure difference, right? A is top, B is bottom. Pressure at A at the top, pressure at B at the bottom. So we can kind of rearrange our equation to do P top minus P bottom. So if PA is top and PB is bottom, then we can say PA minus PB will give us that delta P, which is the P top minus P bottom, right? That's the idea here to kind of figure it out. So top is one pressure point, bottom is another pressure point. When we find the difference between them, delta P, it's PA minus PB. So that's like that part of the hydrostatic pressure equation. But before we start rearranging things, we want to plug things in first just so we can kind of visualize everything. So PA and PB are unknown to us because we don't have any idea of their pressure values. But we do know information about like the densities and the heights and stuff like that. So for the density of blood, right, they said it was 1,050 kilograms per meter cubed, right? So 1,050 kilograms per meter cubed times 10 meters per second squared for gravity and times height at A. Well, one thing I will warn you about when you're doing these types of problems is that how you want to define height, basically. Because this H, right, it doesn't necessarily always have to mean height per se. It could also mean like depth. But you have to be really careful when you do that because then you have to make sure that everything else kind of matches with that definition. So just to be clear, like if I were to say PA plus PGHA, right, pressure at A plus height at A. Well, if I'm saying height at A, height indicates like, if I say like, oh, I'm like 3 meters, like if I have a height of 3 meters, right? Does that usually indicate going upwards or downwards? Just from just a very general kind of sense of the term. Like if I said, oh, I went 3 meters, or I had a height of 3 meters or something like that, right? Or I was up at a height of 3 meters. Upwards, right? So it generally denotes going upwards. And so if you're using height A, if you're defining that as H as in height, then it would indicate that you're upwards a certain distance from a specific point. And so from B, you're upwards a height of 11.2 centimeters, right? Alternatively, what you can do is that you can say, well, I can make the top my initial height, basically, and anything downwards would be like my depth. So HA in that case would be 0. HA would be 0. And then HB would have to integrate that depth there, the 11.2 centimeters. So that's kind of the difference between height and depth. But don't even like worry about that. That's just to help you kind of understand the difference there, not to make that mistake. But whenever you're doing any of these problems, just always make sure that you start kind of like from the bottom and you go upwards. Right? Start from the bottom and go upwards. It just helps to visualize that and make that the actual height instead of like thinking about it as depth. So from the bottom upwards to point A, you're at a height of 11.2 centimeters, right? Which is 0.112 meters. Then at point B, it has another pressure. We don't know that anything about that yet. But HB, if we're referring to this as our initial height, and we go from downwards to upwards, right? What is the height at point B? 0, right? So if height is 0, then this whole term goes to 0. So you're just left with PB on the right-hand side here. So this goes to, HB is 0 because this is your 0 point basically. 0 meters. This is 11.2 meters up here. Or not 11.2 meters, centimeters, my bad. 11.2 centimeters and 0 centimeters up here. Or down there, right? So in that case, now we're just looking for the pressure difference, right? We said the pressure difference was top minus bottom, PA minus PB. So if we do that, PA minus PB, we subtract over, and then we have to subtract over this term, then we can see that delta P is equal to PA minus PB, and that's equal to like negative of this whole thing because you subtract it over. So it'll be like minus 1,050 kilograms per meter cubed times 10 meters per second squared times 0.112 meters. Right? So then your delta P, once you calculate that out, you should get around 1,176 pascals, negative at least. So the pressure dropped by 1,176 pascals. Right? So that's the idea there. Yep, negative 1,176. So that's your pressure drop from bottom to top. So think of top there being like your final position. This is your initial, right? So final minus initial, top minus bottom, A minus B, B for bottom. Right? So if I take A minus B, I should get this stuff here. So if I do PA minus PB, then I'm left with PA minus PB plus this 1,176 pascals. If I want to isolate for this, then I subtract it on the other side. So PA minus PB is equal to negative 1,176 pascals. So there should be a pressure drop of 1,176 pascals. Does that make sense? Make sense for everyone else as well? Any questions at all? Okay. Part B, Kimberly earlier said that we could use the continuity equation, right? So Q1 is equal to Q2, A1V1 is equal to A2V2, right? So part B says one of the arteries has a stenosis, a narrow section at the top, where the diameter drops to 3.4 millimeters. By what amount does the pressure drop now? By what amount does the pressure drop now? So now we're trying to figure out, once again, delta P, which is P top minus P bottom, with a difference in area, basically. Because if the diameter narrows, you go from a really big diameter to a smaller diameter like this, right? The area changes. Why does a change in area matter? What would a change in area do? So, yes, and when you have a decrease in area, right, you actually tend to have a decrease in pressure. And I'll explain why here in a sec. And that's why I was teaching you guys about static versus dynamic pressure. But in terms of at least like the continuity equation, Q is equal to A times V, your speed there, your velocity. If I were to change up the area, decrease the area, how would that affect velocity, or how would it affect flow? So it wouldn't decrease Q, because remember, for the continuity equation, our goal is to maintain the flow. So we want to make Q constant, right? So if we want to make Q constant, if I decrease this area, how do I keep the Q constant? Yes, you increase the speed, the velocity, right? So let me write this with a smaller v so it indicates that it's velocity, right? So if I increase the area, or my bad, decrease the area, then I increase the velocity or the speed to keep the same Q. So if I go from 6, right, let's say the flow is 12, right, and my area was 6, then I have to be going at 2 meters per second, for example. Well, what if I drop down the area to 4, right, and I want to keep that same flow of 12? Then I have to speed up from 2 to 3 meters per second. That way I keep that flow of 12. So 12, if I had an area of 6, then I'm traveling at 2 meters per second. Well, now if I have that same flow that I want to maintain, which is 12, right, then if I drop the area down to 2, for example, then I have to increase my speed from 2 meters per second to 6 meters per second to maintain that 12 value, for example. And so we know that the area is decreasing here because the diameter drops to 3.4 millimeters, right, from 5.2. So there's a decrease in diameter. If diameter decreases, well, diameter is equal to 2 times radius. So then radius decreases. If radius decreases, then area, which is equal to pi r squared. If radius decreases, then the area decreases. If the area decreases, the velocity has to increase to maintain the same Q. Oops, I wrote Q. There we go. So, with that being said, because of that change in area, because of that decrease in area, because of that increase in velocity, well, an increase in velocity would now change like some pressure values that we have here. And so this would have to factor in which equation? Which equation factors in velocity along with pressure and all of that stuff? I'll give you a hint. It starts with B. Nope. No one remember Bernoulli? All right. Well, Bernoulli had this awesome long equation, right? Which was a combination of the hydrostatic pressure equation and another term, which was the dynamic pressure that I mentioned earlier, right? So it goes PA plus rho GHA, right? That's your static pressure. That's your pressure just of a liquid, static, no motion, plus the dynamic pressure of a liquid, right? So that's half density, rho, V squared, right? And that's the velocity at A. You do the same thing on the other hand side but it's the pressure at B plus the height at B plus rho GHB, right? And then it factors in the speed at B, right? So the idea here is that if you were to think about things, because the issue here is like using your intuition with physics. So I've made this mistake so many times. And this is why I didn't really understand this fluid stuff until I separated it out into static and dynamic pressures. But the idea here is that if you were to narrow an artery, for example, or if you were to squeeze on a hose, right, that was spraying water, at least this is what I would think. I don't know if you guys have the same intuition or not, but it seems like it should make sense that if you were to squeeze on something, you're increasing pressure on it, right? It seems to make sense that if you were to squeeze on an area, if you were to decrease that area, where now it's instead of being this wide, if you were to squeeze it, right, now becomes this wide, right, where it's very narrow, a blocked or clogged artery. It seems like there would be a lot more pressure in that sense, right? Just based on our colloquial definition of what pressure is. If you're under a lot of pressure or high stress, feel like everything's kind of pressed on you and you're just squeezed and you're just in this tight position, right? So that's what you would normally think. But if you go to this equation here, Bernoulli's equation, kind of think about it in terms of static and dynamic pressure, well, think of everything just being conserved, right? Everything has to be conserved. So if I were to say what do I want to say? So instead of doing this up and down example here, if I were to let me see if I can go back to the one of the lectures here. So this is what I want to get to. It's called the Venturi effect. And so basically what's going on here is that this point and this point, for example, they're at the same height, right? This is the same height here as this is the same height there, right? If we were assuming that you go, well, not downwards, but if this is our initial point and this is a height of 10 centimeters, this is also a height of 10 centimeters, right? They're the same height upwards. So if there's the same height, if we go back to the equation here, if this is the same height, it's the same fluid, it's the same gravity, this term should be the same as this term, right? That's for sure. These two terms are the same, right? Now, if we were to refer to the continuity equation, right, we know that if I decrease this area, if this artery suddenly became clogged, if this hose, right, I started pressing on it a little bit or squeezing it, then I know if I want to maintain that same amount of flow, Q has to be the same. If I decrease area, I have to increase velocity. If I increase area, I decrease velocity to maintain the same Q, right? So if I decrease area here, like that example, then I have to up my velocity, right? So if I up my velocity, if my velocity increases here, then this term is bigger than this term. This term is bigger than this term. Well, these two terms are the same. So let's say if we just did it in simple numbers, if this term ended up to be 2, and this term is also 2, because remember, it's the same fluid, it's the same water, it's the same blood, same gravity, and they're at the same heights, right? If we did, this was an artery that we just kind of looked at longitudinally, right? So if this is the same height as this height right here, then that rho GH term should be the same on both sides, 2 and 2, for example. Now, we already said that if you squeeze on it, right, or if you just clog the artery, for example, then you decrease area and you increase speed. Well, if speed is larger here, assuming the same densities, then this might be 4 and this might be 3, for example, for those two values. Well, we want to make sure that with this equal sign, that this left-hand side is equal to this right-hand side. And so if this is 2 and this is 2 based on the fact that they're the same height, then this is 3 and this is 4 because as you squeeze, right, you have to have increased speed. Well, if I want to maintain the same value on either side, what do you notice? 2 and 3 is 5, right? 2 and 4 here is 6. let's say if I said that the value is going to be 10 on the left-hand side and the right-hand side is going to be 10. So if I want 10 on the left-hand side here, this has to be 5. If I want 10 on the right-hand side, this has to be 4. So you can see here that the pressure at point B, the pressure at B, will be lower than the pressure at A. So if this is A and this is B, right, they're the same height. Here you have an increased velocity. Here you have a decreased velocity, right? So if there is an increased velocity at point B here because of that squeezed area, if this term gets bigger, while these two terms are the same, this term is smaller because of this lower velocity, then the pressure actually at point B, at that squeezed part, should be lower than the pressure at that more relaxed part. So that's where the intuition kind of falls apart. Because you would assume that if you squeeze on it, you decrease the area, right? It seems like there should be more pressure, quote unquote, right? But in reality, there is lower pressure. So you can see here that if your dynamic pressure were to increase from 3 to 4, right? If your dynamic pressure increases, then your static pressure, this component right here, has to somehow decrease. Well, the only aspect of it that decreases is just the absolute pressure here, which is the pressure of the specific point. Because these two terms, assuming the same height, they're going to be the same. But that kind of is a very conceptual explanation of what's going on here, just to kind of explain that. But if we have that change in diameter, right, we should see a change in radius, like I said before. And so if we say Q1 is equal to Q2, we have the same flow. So A1 V1 is equal to A2 V2, right? Well, A1 is going to be pi r squared, right? So if we said the diameter, what did I want to say? Shoot, I almost forgot. Yeah, so pi r squared, pi r squared. So if we're going by the initial diameter here, if the first point is the relaxed point, right, of the diameter of 5.2, then that has a radius of 2.6 millimeters, right? So 2.6 millimeters, if we convert that to meters, right, because we want everything in SI units, then we should see that it should be 0.0026 meters, and then we square that, pi r squared. That's our area for the relaxed part. And then it has a speed of 0.5 meters per second. Right? Because they said that the narrow section is at the top. So the bottom section is the relaxed part. And then we have pi r squared again, but instead of 5.2 millimeters for our diameter, it's 3.4 millimeters. So our radius now is 1.7 millimeters. And that's going to be 0.0017 meters. And then we square that, multiply by our velocity that we have to figure out now. Because we decrease this area term from this to this, right? Because we decrease the radius. So then we have to figure out what this new velocity is going to be. Well, we already said if we decreased area, we have to increase velocity to maintain the same flow for that continuity equation. So you end up with a velocity of 1.17 meters per second at point A, or at the top, right? At the top here, this narrow portion. So that gives us our velocity, right? Now we want to see how that change in velocity is going to factor into the Bernoulli equation. And so you have that PA plus rho GHA plus half PV squared, PB plus rho GHB plus half PVB squared, PVA. There we go. So PA and PB, once again, they're unknown. We have to figure them out, or at least figure out the change in the pressure, top minus bottom, right? And so we can just figure out the rest of these values here. Well, we had, what was it? Let me just, I don't know if I should copy. No, it's not worth copying. So for the density, it was 1,050 kilograms per meter cubed for the density of blood times, I'm going to forego some of the units here, 10 meters per second squared times height. At A, that was the 11.2 centimeters, which is the 0.112 meters. And then plus 1/2 times the density again. And then times the initial speed through that relaxed point. And then square that, right? And so now, on the right-hand side, you still have that PB that we don't know. Still have the same 1,050 kilograms per meter cubed for our density, times the same 10 meters per second squared for our gravity, times the height at B. Well, the height at B should be 0, right? The height at B is 0. Because they're at the bottom here. That's our reference point, essentially. So that whole term goes to 0. And then we're left with half times the density, 1,050 kilograms per meter cubed, times the new speed, right? Or not the new speed, my bad. This would be... So I think I messed that up earlier. I said that this was the speed of the relaxed point, or the bottom. This is the faster speed at the top, my bad, through the narrow point. I misspoke when I said that. This is the relaxed point right here, PB, because it has a smaller speed. So once you kind of solve out all of this mess and you kind of isolate for P top or PA minus PB, you essentially take this stuff here, you add it up together, and then subtract it from this stuff there that you added up together. And so you end up with somewhere around, so this is delta P, somewhere around like 1,763.4 pascals, and I believe it's negative 1,763.4. Because it only makes sense that there should be a pressure drop as well because of that increase in speed, like I said. Does that make sense so far? I know that was like a very long run around to everything, but I wanted to make sure that you guys understood what's called the Venturi effect. I'm not sure if you guys have used Venturi flow meters in your lab yet, but it's like that one, it literally just looks like this. Like, have you guys like used these tubes before? Like, I swear there's a lab for this. No, not yet. Okay, but hopefully, like, that kind of helps understand, helps you guys understand that like idea of separating things into static pressure versus dynamic pressure. And so, like, basically, if this speed over here increases, right, assuming these two terms are the same, then the pressure at B has to be lower than the pressure at A. To be a lower pressure. Now, the thing is, yeah, go ahead. Does someone have a question? Mm-hmm. Yeah, so the different radii, yeah. So I have, they said the diameter for the relaxed part for the bottom was 5.2 millimeters. So 5.2 millimeters as your diameter. Well, we know that diameter is equal to 2 times radius. So if I divide by 2, my new radius should be 2.6 millimeters. And then if I just divide by 1,000, right? Divide by 1,000, so I just move 3 decimal places to the left. So 2.6, 1, 2, 3. That gives me 0.0026 meters. That's how I converted. And then for the decreased diameter, right, it went from 3.4 millimeters as my diameter. Diameter is 2 times radius, so if I divide by 2, that gives me 1.7 millimeters for my radius. And so converting from millimeters to meters, right, you just divide by 1,000. So that's just moving from 1.7, you move 3 decimal places to the left. So 1.7, right, you go 1, 2, 3. So 0.0017 meters for your radius there. Yeah. But, I mean, when you have, though, different values like these rho GH values were different because this was 0 at the bottom and this had a specific value, right? Then you would have to, like, use the equation and figure things out to be able to realize, like, whether or not you have a larger or smaller pressure at different points because there's different heights at that point. But otherwise, if you're at the same height and you simply just decrease the area and increase the velocity, then you should observe a lower pressure at the point that was constricted. Sound good? That makes sense for everybody else as well? Any questions at all about this stuff? Thumbs up, thumbs up. Okay. We're slightly behind because I think this problem is going to be long, but actually, it's not too bad. It only gets bad towards the end, sort of. But it says problem 3: open tube pressure gauge. A pressure gauge can be made with a vertical tube that is open to the atmosphere. The higher the pressure at point A at the bottom of the tube, the higher the water in the tube will be. Right? So the higher the pressure at point A, the higher the water in the tube will be. So part A, they're asking, what is the speed of the water as it enters from the left? What is the speed of the water? So they're giving us the area here. This cross-sectional area is 10 centimeters squared, and this cross-sectional area is 5 centimeters squared, and they give us the speed at that cross-sectional area. So let me see if I'll call on someone here just to keep things fresh. Okay, Zahra, do you know how to kind of start us off for this part here if we're trying to figure out the speed of the water as it enters from the left? For like the this one right here. So we have our velocity, right? Sure, yeah, we do have I mean, we can get the density of water. Yeah, that's absolutely right. But if we wanted to kind of use like this part right here, like the half density VA squared, right? We'd have to kind of include the rest of this stuff. And so let me try to think. So like, I think we could possibly do it, but I think it would be a little bit more difficult because you have to like compare the height at A to this unknown height, for example, or even like use one of these heights here somewhere, right? But like I said, we do have area though. We have area and we have speed, at least for this section here. So if we wanted to figure out the speed at point 1 versus the speed at point 2, exactly, and right, and Kimberly was on that too as well, right? So we can use the continuity equation, right? So if Q1 has to equal Q2, the flow has to be constant throughout the whole thing, right? The flow is always constant. Then we know that area 1 times velocity 1 has to equal area 2 times velocity 2. Well, we have the second area, which is 5 centimeters squared, and we have the second velocity, which is 4 meters per second. So what we can do is simply just say, okay, well, 5 centimeters squared times a speed of 4 meters per second versus an area of 10 centimeters squared. Well, what's the velocity for the first one? And so we can simply just kind of divide things over, and we can get our V1 there, right? Which is the velocity or the speed as the water enters from the left. Now, you might be wondering, like, why are you mixing and matching like centimeters and meters, right? Well, in this type of equation, right, as long as like the values on either side are the same, it's fine, because if you have centimeters squared and centimeters squared, once you divide them over, then they will just, the units will just cancel out, and then you're just left with meters per second on either side. So once you isolate for V1, you should see that it's equal to 2 meters per second. So if we have a larger area here, much larger area, we should see a lower speed. If we start to constrict that area from 10 to 5, we should see a higher speed. Things go faster, right? If you squeeze on that like garden hose, then the water should come out a lot faster, for example. So that's the speed as it enters from the left. Now, for part B, they're saying the diagonal tube has the same cross-sectional area as the outgoing horizontal opening. What is the speed of the water at a height of 2 meters? So they're looking at a height of 2 meters, right? Well, roughly from like the beginning, let's say that like, yeah, the drawing is a little bit off, but like roughly from the beginning of the diagonal to the top here is 4 meters, right? From the bottom of the diagonal to the top of the diagonal, it's 4 meters. And so they're asking, what is the speed of the water at a height of 2 meters? Well, if the diagonal tube has the same cross-sectional area, so this area here is equal to this area there, what should we see for the speed if they're the same area? Exactly. Awesome. Yeah, the speed should be the same. Because remember, we want the flow to be constant everywhere, right? Q1 has to equal Q2. Wherever you set your Q1, wherever you set your Q2, the flow has to be the same. So if we set Q1 here, Q2 there, the flow has to be the same. If we set Q1 here and Q2 there, the flow has to be the same, right? If we set Q1 here, Q2 there, the flow has to be the same. So Q1 is equal to Q2. That's equal to A1 V1 is equal to A2 V2, right? Well, if A1 is equal to A2, right? A1 is equal to A2 because diagonal has the same cross-sectional area as the horizontal. So we can say like A diagonal is equal to A horizontal. Then V1 is equal to V2, right? So A diagonal is equal to A horizontal. So V diagonal has to equal V horizontal. And V horizontal already is given to us, right? They said it was 4 meters per second. So this is equal to 4 meters per second. So V diagonal is equal to 4 meters per second. So excellent job, Matthew. So that's B. Does that make sense for everyone? Yes. Okay. Part C now is asking what is the absolute pressure at the point A at the bottom of the vertical tube. So absolute pressure at point A. So if we want to figure out the pressure at point A, how could we do that? Keep in mind of the situation that we have going on. Is the fluid moving, or is everything constant? That will indicate especially which equation to use. Let me see here. So I'll call on someone if no one wants to volunteer. So I see just a person. Okay, I can repeat the question. So they're wanting to ask us about the absolute pressure at point A. So for the absolute pressure at point A here, keep in mind that we have a fluid here, and make sure that you're kind of keeping in mind the situation. So do we have a fluid that is moving, or is it static? So it's moving, right? Now, since it's moving, if we wanted to figure out pressures related or pressures at certain points, right, with motion of a fluid, which equation should we use? If we want to relate pressures with the pressure of moving fluid as well. The one that starts with a B. Excellent. Bernoulli's equation, right? Just think Bernoulli like B, like big boy equation, like it's just like a massive equation, right? It's just the big boy equation. Let's call it that. The big boy Bernoulli equation. So we have PA, right? Like let's actually say PA like this, right? Oh, wait, can you guys hear me still? Because I think my headphones just died. Okay, cool. So PA plus rho GHA plus half rho PVA squared is equal to PB plus rho GHB plus half rho PVB squared, right? So for the pressure at point A, this is the absolute pressure here. This is when we say PA, like this part of the equation is known as the absolute pressure. Alternatively, you can write it using gauge pressure if you wanted to. And just remember that gauge pressure, right? Gauge pressure is equal to your absolute pressure minus the atmospheric pressure. And the atmospheric pressure is 1 atmosphere or 10 to the 5th pascals. So if you have like something like, 12,000 pascals or something like that, right? Then you just take minus 10 to the 5th, and that's your gauge pressure, right? But in this sense, it's almost always absolute pressure. But sometimes, like, definitely expect them to ask you about gauge pressure and to use that equation with gauge pressure. All you'd have to do in that case is just then to subtract 10 to the 5th from that aspect of the equation. Sometimes too, they'll ask you to put everything in terms of gauge pressure. So like, if PA was at the top here, what is the pressure at the top here? At this surface here, what is the pressure? 1 atmosphere, right? That's atmospheric pressure. So 1 atmosphere, which is the same as 10 to the 5th pascals. If I were to put things in absolute pressure, then PA would be 10 to the 5th. If it was gauge pressure, what would PA be? So remember, gauge pressure is 760 millimeters of mercury, 760 torr would be your atmospheric pressure as well. But if P gauge is equal to your absolute minus your atmospheric, right? Well, if your absolute just so happens to be your atmospheric, then what should be your P gauge? If the absolute is equal to the atmospheric, then yeah, P gauge should be 0 in that case. So just keep that in mind if they're asking for gauge pressure stuff and you just so happen to have a point that is in contact with the atmosphere or has atmospheric pressure, then if they're doing gauge pressure stuff, then this would go to 0. But if you use gauge pressure on one side, just make sure to use gauge pressure on the other side as well, because otherwise you're going to get like just weird answers. But they're asking just for absolute pressure, so we'll keep that in terms. Now, if we have point A, which is what we're going to consider the bottom of the tube, then if it's at the bottom, what should our height be? 0, right? So this whole term will go to 0. It's not worth writing out. HA would go to 0. Now, PB, right, some point B, we can choose the point. What point is very easy to access, or what point do we kind of like have a lot of information about? Yeah. Well, we have point A, right, that we're trying to figure out. We know that the height at point A is going to be 0 because it's at the bottom, but we also have this ending point right here, which has a height of 4 meters, right? So that diagonal tube from here to here basically is 4 meters. And so we can say that the height at the top of the diagonal tube here is going to have a height of 4 meters, right? Okay, now both headphones have died now. So hopefully you guys can still hear me. So sorry for the inconvenience. But basically for our height here would be 4 meters, right? So if we want to do, what is it? So it's here, the density of water is 1,000 kilograms per meter cubed. Gravity is 10 meters per second squared, and the height is 4 meters, right? And then we can also plug in values like the density here, again, for the dynamic pressure part, and your velocity here, VB. That's going to be that 4 meters per second, and then we can square that. That was the velocity at B. Right? And so PA, once again, is unknown. That's what we're trying to figure out. And we have half times 1,000, which is the density of water, times VA squared. VA, we already determined that to be 2 meters per second, right? That was the speed of the water coming in. So now we're left with PB. Well, we have PA and PB that are apparently unknown. Yeah, the recording is still working, by the way. No worries. The recording is still working. But for PB now, how can we figure out PB? Because PA is the thing that's unknown, right? So we have to know PB. What information tells us anything about PB? Or at least maybe what can we infer, at least maybe from the drawing of the graph here? So how can we figure out PB, the pressure at point B, right? So that was at the top here of this diagonal tube. So, or at least we could maybe say it's here, because here doesn't really make a difference. They're the same height. So right here, if we were to choose that as point B, what would the pressure be at that point? Atmospheric, right? It's in contact with the atmosphere. It's contact with the air. So this should be that 10 to the 5th pascals that we were talking about. So this should be your 10 to the 5th pascals. Right? And so if we add all of this stuff up and solve for PA, so we have this atmospheric pressure at point B, because it's in contact with the air here. Then we add it to rho GHB plus half rho VB squared, set it equal to this left-hand side here, right, which is the pressure at A plus the dynamic pressure as well, right? And we know that the height there at the bottom is 0, so that goes to 0. Once we solve for A, we can get 146,000 pascals, right? That's that. Exactly, yep. Since it's open to the atmosphere, right here, that should be our atmospheric pressure, 10 to the 5th pascals there. Sound good so far? Okay. Part D now is asking us what is the height h of the water in the vertical tube. So the height of the water in this vertical tube right here. Well, we don't see any indication of motion throughout this vertical tube, right? We're just looking at differences in pressure from here to here, right? And that's only differences in height. So what equation do you think we're going to use if we're just looking at differences in pressure just with fluid that is going to only differ in height and that there's no flow anywhere along this height? Or there's no movement of fluid anywhere along that height, basically. Yep, hydrostatic pressure equation, we can use that. So we have PA plus rho GHA is equal to PB plus rho GHB, right? Well, pressure of A, we already figured that out. That's 146,000 pascals. And we said that, okay, we can determine that our A here is at the bottom of the tube, basically. That's our bottom point. And then anything upwards is height. So height indicates like moving upwards, right? If you're at a height of 3 meters or something, that's the denotation for it. Or at least that's a connotation for it, I guess, yeah. So, but that's going to be height of 0 there at the bottom, and then anything upwards will have another height. So this height is 0, so that whole term goes to 0, and then we're left with PB, which is the point at the top here, because we want to figure out what's the difference between the pressure here and there. Well, PB plus rho GHB, HB is what we're trying to figure out, right? Now, what is the pressure at point B? What is the pressure here? Yeah, 1 atmosphere, right? And that's going to be 10 to the 5th pascals. So we want to make sure that everything is in units of pascals. Very rarely do we ever use like atmospheres and stuff for these equations. So 10 to the 5th pascals is your pressure at point B. And then you have your density of water, which is 1,000 kilograms per meter cubed, times your gravity, 10 meters per second squared, and then times your height that we want to figure out at point B. So if you solve that out, you should be able to get 4.6 meters for the height at B. So this height here from there to there goes upwards of 4.6 meters. Does that make sense? Yes, okay. Now we're just left with parts E and F. So for E, is asking if the inflow pressure at the left entrance increases, then the height of the water in the tube would increase. If this height is changed to h nu is equal to 2 times h, what would the new outflow speed of the tube be? So if they double the height, what is the new speed, the new outflow speed of the tube? So Let me kind of think about this one for a second here. So if they want us to increase the pressure at that left entrance, then the height of the water in the tube would increase. Okay, so this height here increases if we increase the inflow pressure. And if this height doubles, then we have to figure out the new speed. Okay, that's not bad. So remember here, our PA equaled the pressure at point B plus rho GHB, right? So essentially they're asking, okay, what if we doubled HB? What happens? So if we just took this 4.6 meters and doubled it, well, then we would have a different PA, right? We'd have a different pressure at point A. Because remember, they also said the higher the pressure at point A at the bottom of the tube, the higher the water in the tube will be. Vice versa as well. If we double the height in the water, we should see an increase in the pressure at point A. So if we want to look at the new pressure, PA, that new pressure at PA, let's say that might be 200,000 pascals instead of 146,000. If it's 200,000, right, then if we plug that into the Bernoulli equation, if this is now all of a sudden 200,000, right, then we should see basically a change in the outflow speed, right? The speed here at the end. Right? So that's the idea there. Now, the only issue here that we see is that if we don't know the speed at point B, then how should we know the speed at point A? So if we doubled this point, this HB, if we doubled it, we can figure out what PA is. Once we have PA, we can add it to rho GHA and half rho VA squared. Well, what's VA? Remember, VA and VB, we kind of figured that out in part A, right? They said VB is 4 meters per second. And VA was 2 meters per second, right? At the beginning here. Now, we're trying to figure out this VB. We're trying to figure out the new VB. However, if this changes, if the VB changes, then the VA also has to change, right? Now, what remains constant? If your speeds change, if we're just increasing pressure and stuff, what remains constant about this whole thing? Let me give you a hint. Area, excellent, right? So area remains constant. It's the same type of tube that we're flowing through and everything like that. So assuming the continuity equation again, if Q1 is equal to Q2 and the area stay the same, well, if this V2 increased, V1 should increase as well. So if I doubled the velocity, right, if V2 is 4, for example, like if V2 was initially 2 meters per second and I doubled it to 4, what should happen to my V1? Or at least, let's look at here. So if I said V2 was 4 meters per second, right? 4 meters per second. And then I doubled it from 4 to 8. What should happen to my V1? So if A1 is the same as A2, right? So A1 V1 is equal to A2 V2, where A2 is also equal to A1. If V2 was doubled, so it becomes A1 times 2 times V2, and you have A1 V1, right? Then in order to have the same continuity, or not same continuity, or to have the same flow, what should I do to V1 here? So if I were to double the speed here on the right-hand side, right? If I doubled the speed and my areas are the same, what should I change to the first speed? So on the left-hand side here, how should I change it? You double it, right? You double it as well. So in that case, right, for part E, we don't know this new speed. We don't know it. We don't know this new speed over here. V new is no longer 4. We don't know what it is, right? But what we do know, right, is that if we doubled the right-hand speed, we have to double the left-hand speed as well, right? We have to double both. Why? Because if we were to double here and here, while the area remains the same, that helps us maintain the constant flow and the continuity equation, right? So all we know then is that this V new, whatever it is, it has to equal like, what is it called? What I want to say? So yeah, if we doubled V new, for example, then it'd have to equal like, oh no, I got the other way around, my bad. So yeah, if we doubled V new, then the left-hand side, right, half of it has to be equal V new. So that way, V left is equal to 2 times V new, for example, right? So we have to kind of look at things that way. And if we were to go back to the continuity equation to write things out so you guys can see it a little bit better, we know that A on the left-hand side times V left is equal to A on the right times V right, right? So this V left is what we're trying to figure out here. Or not my bad. We're trying to figure out the V right. That's what I meant. But we want to write things in terms of only V right. So we can say that V left is equal to A right times V right divided by A left. That way, when you write your terms out and everything, when you write this equation, the goal here is to have just one variable. So I don't want to have V left and V right. I want to be able to figure out V right, but write everything in terms of V right as well. So I have V left here and V right. I want to write V left in terms of V right. So maybe V left is equal to 2 times V right. So I want to write it in terms of that. So I want to like do a substitution essentially. And so I know that the velocity of the left, well, the area of the right was equal to 5 centimeters squared. And the velocity of the right is what we're trying to figure out here. And the area of the left was 10 centimeters squared. Those areas didn't change. So you can see here that V left is equal to half of V right, because 5 divided by 10 there is 1/2. So you can see that the velocity of the left-hand side should be equal to the half of the velocity on the right-hand side, based on the areas and based on the continuity equation. And so we're going to write our equation, we're going to write our velocities all with this V right. So instead of saying half PV left squared, we can say half PV right divided by 2 squared. This V right divided by 2 is the same thing as saying V left. We do this in order to maintain like all of the right variables that we're looking for, because everything else will have a value. Like we'll be able to calculate out rho GH or rho GHB here and PB, for example, we're going to have set values for those. But VB, or V right, essentially, right? We won't have a value for that. That's what we're trying to figure out. But we can't figure it out if there's also a V left on the left-hand side here. That'll complicate things. So we want to write everything in terms of the variables that we're looking for. We don't want to have any other extraneous variables to look for. So by rewriting it this way using the continuity equation, we can say that the area of the left-hand side times the velocity of the left-hand side should equal the area of the right times the velocity of the right. That tells us that the velocity of the left is equal to area of the right times the velocity of the right divided by area of the left. So 5 centimeters squared divided by 10 centimeters squared times the velocity of the right tells us that the velocity of the left is equal to half times the velocity of the right. And you can see that here at the beginning where 4 meters per second, right? The speed was 2 meters per second at the left. So speed of the right was 4 meters per second. Speed of the left was 2 meters per second. So exactly half of it. And that relationship is maintained here. So we can see that the left-hand side speed is going to be half the right-hand side speed. So once we write down this equation, right, we have PA plus half PVA squared, right? Or we can say P left plus rho GH left. I actually wrote that the other way around, my bad. And then we have rho B plus rho GH B plus half rho PV, or my bad, rho V right squared. And so we said from before that we don't want to write things as V left. We'll write it as V right divided by 2. So that way you can see here that this will eventually, the V right will be the only variable that we're looking for at the end. Whew, okay. So for PA, we said that we can figure it out using PB plus rho GHB, right? Because it's not 146,000 anymore. They said they doubled the height. So if they doubled the height, this 2 times HB, then we're going to figure out the new PA. So we can say PA is equal to PB plus rho GHB. That's 10 to the 5th pascals plus 1,000 times 10 times height. That's 2 times the height of B, which is 9.2 meters. So 4.6 times 2 is 9.2 meters. And this gives us a new pressure at point A of 192,000 pascals. That's our new pressure at point A. So remember, they increased the height, they doubled it. So if they doubled the height here, based on the information they also gave us, the higher the water, the higher the pressure. So if we double that height, we're going to increase the pressure here of point A. So from this goes from 4.6 to 9.2 meters, because it doubled it, and now we have a pressure of 192,000 pascals. So 192,000 pascals plus half times 1,000, that's the density of water, times V right divided by 2 squared plus 1,000 times 10 times height of the left, and the height of the left-hand side here, actually I didn't even have to write it down. The height here at point A is what? What is that height going to be at point A? 0, right? So if that's 0, then this H here goes to 0. So we don't even have to write it down. Now, point B here, we said that it's in contact with the atmosphere. So that should be an easy 10 to the 5th pascals there. Rho GHB, we said that's 1,000 times 10 times a height of 4 meters, right? That was the height of that diagonal tube. And then, let me just make things a little bit smaller here. And then that's plus 1/2 times 1,000 times V right squared. So the reason why we did this stuff over here is that now we have this is a value, this is a value, this is a value that we can all calculate. All we're left here, the only variable in play is the velocity of the right, or the speed of the right, which is the new outflow speed that we're looking for. So if we go ahead and solve that, if we do this whole thing, we should end up with 11.78 meters per second. Takes quite a bit of like mathematical manipulation for these types of problems, but yeah, this is like the key step for it. If you can figure this part out to make sure that there's a relationship between like these values, right? Because the thing is, like, you can kind of work backwards a little bit too. So if you have this whole big equation right here and you write things out and you're like, oh, half p or half rho v left squared, and you have v right, well, then you're like, okay, well, I want to figure out v right. How the heck am I supposed to figure out v left? Well, then you have to go back and think about, okay, well, what's the relationship between v left and v right? So if you can figure out that relationship is constant because of the constant flow, because of the continuity equation. If you can relate those two things, then you can write one velocity in terms of the other, and then have just one variable that you're looking for at the end. Oh my God, that hurt. That took way longer than I was expecting. It was a very, very long problem. Does that make sense? I mean, I know that's hell, but I just feel bad because like this, it's like I know it kind of seems like a lot of like mathematical manipulation, and you kind of have to really think about what's going on to figure it out. But I mean, I just hope they don't pull something that's this like intense on the exam. But I mean, you really just have to expect for them to pull this stuff. Like they will definitely, there's going to be 1 or 2 problems on this stuff on the exam. So just be ready, practice a lot, figuring out relationships between these variables, what happens if you increase or decrease another, and then this continuity equation stuff is so crucial. But yeah, that's part E. Part F is if all of the water is replaced with oil with a density of rho oil is equal to 0.75 rho water, and the vertical tube is filled up to the same height, what is the new pressure at point A? So if they're telling us they replaced all of this water here with oil, right? And that oil is 3/4 the density of water, basically. Then, and if we fill that vertical tube up to the same height, what is the new pressure at point A? Well, remember, we said that to figure out the pressure at point A, that's dependent on the pressure at point B, which is the top here, plus rho GHB. Well, this rho is going to be different. The height is going to be the same. Pressure should maintain the same as well because it's atmospheric pressure at the top. But this density is going to be different because of the oil, right? So rho oil is equal to rho water times 0.75, and the density of water is just 1,000 kilograms per meter cubed. And so this gives us a density of 750 kilograms per meter cubed for oil. So the pressure at A, that point A, should be equal to the pressure at B, which is the top, right? Pressure at the top there. This is A, this is B at top, and that's the atmospheric pressure because it's in contact with the air. And that's plus rho GHB. This should be 10 to the 5th pascals. This is not 1,000 because this is density of oil now. This is 750 kilograms per meter cubed times 10 meters per second squared. And then times the height, and that was the same height. Remember that was the same height of D here, which is 4.6 meters. So if we do all of that, that helps us figure out pressure at A, which is 135,800 pascals. That's the absolute pressure there at point A. Now, if, for example, we wanted to figure out gauge pressure, like I said earlier, then we just take this thing minus 10 to the 5th pascals, because gauge pressure is equal to the absolute pressure minus 1 atmosphere, or 10 to the 5th pascals. It's just minus your atmospheric pressure. So this minus 10 to the 5th pascals will give you your gauge pressure in that sense. But like, I think that's it for part F as well. Any questions about problem 3 at all? Anything you guys weren't quite sure about or wanted me to kind of like just hammer again? Because I know this is a very, very long problem, very complex, and very time consuming and very draining. So please let me know if there's any part of this stuff that you don't understand. But question though, like, did the idea of the whole like static versus dynamic pressure kind of help you see and understand things a little bit better? Or not so much? Did it help kind of to confuse you more? Okay, awesome. Sounds like it did. Okay. Yeah. That's something I actually recently learned when I was studying for the MCAT, so yeah. It helped me, so I figured, I was like, okay, well, I might just add that to the lecture, so it might help you guys understand a little bit about what's going on. But that's been it for this written homework. So yeah, I just hope everything is fine with the recording as well, because this thing is like almost 6 gigs. I think it's probably like the longest video I've done. But yeah, that's it. So hopefully you guys found this helpful, and I will also record. I will try my best to find extra time to record like the old quiz review session that I messed up the recording for. So, yeah, I mean, I'll try to find time to like at least record it by myself, and then like go through the lectures and stuff, the lecture slides, because I'm so mad because I had like, that was like probably one of my best lectures. It was very organized, very neat, and like very comprehensive. But what a shame that it was recorded with no audio. So I will try my best to find some time to record that sometime here in the next couple of days. If not, like, I definitely will have it before the exam, just so you guys can use that to review. So yeah, I mean, I think that's it. Honestly, I'm tired, so I'll probably end the recording on that note. Hopefully you guys found this helpful, and yeah, enjoy the rest of your night.